today we'll be talking about mesh processing with hoops and more specifically Polygonica mesh processing toolkit from MachineWorks that we have the privilege of reselling and working with very closely with MachineWorks and being able to represent them in the market and bring that kind of to our TechSoft community. So we'll be focusing on that today. This is meant to be technical. We're going to be looking at some code. We're going to be looking at some slides. There'll be an opportunity for question and answers. It's also meant to be more of a high-level introduction to mesh processing with Hoops and Polygonica. If you want to dig deeper, then we do encourage you to sign up for an evaluation, and we'll walk you through that. So just a little bit about TechSoft. We're driven to fuel 3D innovation. That's really our goal. We either create or resell a number of different software development toolkits specifically for the 3D engineering space. Very few people know who we are at the end user level, but we have over 500 different customers who are bringing software into the engineering space when it comes to analysis or CAD or CAM. 3D printing, we've really seen an explosion of in the last couple of years. And this excites us to see what you guys are doing with our technology. So the cool new things when it comes to 3D printing or working with different people to help make more efficient buildings or cars that don't run on gasoline. That's the cool stuff that we like to celebrate, and we're really grateful to be working with all of you to bring these different products to market and to provide you with the technology that does that. A couple things, we're going to be recording this session, so feel free to take notes, but if you want to kind of follow along later at your leisure with the code, I'll make this available, send out an email to you, and be able to provide that to you. Also, if you have questions, please send them there to the chat, and I'll be checking. There'll be a couple opportunities to ask some questions, and I'm really glad to see that we have a few people from MachineWorks also here online, and if I can enlist them a little bit to answer maybe some of the tougher questions, I might be calling on you guys, but welcome everyone. And Tim, I'm going to mute you. I think everyone else is muted, and we are good to go. So specifically, what are we going to be talking about today is the Polygonica Mesh Modeling Toolkit. This is not something that TechSoft creates, but again, we're very grateful to be working with MachineWorks and their product Polygonica, and being able to be one of besides MachineWorks, the only worldwide channel for providing that technology to the engineering market. What is Polygonica? Well, if we were to distill it, or if I was to distill it, it's a toolkit for processing polygonal meshes. So we're not talking about the boundary representation or let's say traditional CAD data, but we're talking about collections of triangles and polygons, many of which we see coming from STL files for 3D printing, from point scans, from analysis data, and they have a highly efficient tool for processing that and preparing it for a number of different workflows. Primarily 3D printing, but we've seen the ability to use it in a number of other areas as well. So we don't want to exclude other companies or other workflows like collision detection for construction or robotics or mesh preparation for analysis. Dental and medical field really seems like two excellent places where this is being used as well. It's not just for processing polygonal meshes, it's really much more powerful than that. It's a modeling toolkit where you can take modeling like function calls and apply it to your mesh data. And they're doing some really exciting things like feature recognition and thickening of walls that really is more reminiscent of a modeling kernel that you would use to power a CAD package, but really applying it to the mesh data. And it's extremely powerful. This is what I like about it. Very powerful, very easy to use, and it just works. Like when you go to heal a file, it just works. It's been around for a long time. It's based on proven MachineWorks technology. So they're the leader in providing CAM kernels to drive CAM software, and most of the major computer-aided manufacturing software companies out there are using the MachineWorks kernel. It's been in over 20 years of development, and key functionality of that MachineWorks kernel has been applied and kind of pulled out and added to and refined as part of the Polygonica Toolkit. And so this, even though it's been on the market for, Richard and Lynn, maybe 7-8 years, there's been 20+ years worth of developments coming from MachineWorks, powering this toolkit, and just thousands of seats running similar code as Polygonica. That does kind of fit into the technology we have here at TechSoft. So we have a number of platforms. I just want to mention those briefly. That Power Engineering SDKs. Hoops Exchange allows you to read CAD data. Hoops Visualize and Hoops Communicator, the HV and HC there, allow you to visualize it. And Hoops Publish allows you to publish it to 3D PDF or other standards like STEP for 3D printing. 3MF is a emerging standard for 3D printing, and they all work very well with the Polygonica mesh modeling kernel. We will be taking a brief look at some of this technology and how they work with Polygonica later on in our session today. So who's using Polygonica out there? Really, it's the who's who when it comes to 3D printing. So companies like Stratasys, Desktop Metal, 3D Systems, they're all leveraging Polygonica to do mesh modeling and mesh preparation for 3D printing. Other companies that are CAM companies using it as well, or analysis companies that allow you to prepare a mesh for pre-processing and analysis. Robotics companies are using this as well. Visualization companies are using it for simplifying their meshes to allow them to better visualize the heavy 3D mesh data in their graphics. So a lot of different applications and some really big names that are using Polygonica to work with their mesh data. It's a very powerful API. There's a tremendous number of functions to it, but I want to just call out a few key ones that may be of interest to people today. And first and foremost is the automatic mesh repair. And this allows you to take, let's say, a mesh file. We're looking at the top image there is a dental data set. The green edge shows where this mesh, or the green edges show where this mesh have open edges or a hole. So this is not a watertight solid. That's necessary, a watertight solid where all edges of all triangles in the mesh are connected to other edges and triangles. That's necessary to use in 3D printing. So 3D printer needs a watertight mesh. It's also needed for analysis. It's also needed for other downstream operations. So really the first step in many of these workflows is automatic mesh repair. And that's one of the places in which Polygonica really excels, is being able to fix holes, fill holes, similar to here, but also fix other issues that exist in the mesh. And there's a number of those. We'll be talking about them a little bit later. But that's the first step, and what I find quite useful of this toolkit is it just works. It's really fast, and so the number of errors that you get, it just works. The number of errors are very minimal when running their automatic mesh repair. You can run it in an automatic kind of headless way, or you can fine tune it specific for a particular workflow or a particular data set. Next step is, like, once you have this mesh in a form that you can work with, there's a number of different things that you can do with it. Boolean operations. Coming from the MachineWorks space, when you're they model the removal of material, and 3D printing or additive manufacturing, we've modeled the addition of material. But MachineWorks has been very efficient, very good at taking a mesh and modeling how, as you take a tool across a part, modeling how material is removed from it. So that's where the roots come from. They've been able to do that very quickly instead of using a boundary representation or a mathematical model. Being able to model the removal of material from a triangular mesh or a mesh, a polygonal mesh, they found a way to make it much more efficient and do it in real time. Well, that's a Boolean operation. It's a Boolean subtract of a tool from a target. Same thing with Polygonica. Their Boolean operations are exceptionally fast, being able to find intersections, unions, subtractions, using Boolean operations on different parts. And that's important because many times we want to take a collection of solids, be able to Boolean them together, and then print them. Or the other way around, we want to take a solid and remove it from that. Let's say if we wanted to hollow out an object for 3D printing, we would do the same thing. We would, well, the next one here is offset. We would offset the model down, subtract the offsetted one from the larger model, and then using Boolean, and then be able to use that for 3D printing. Of course, there'd be other parts of that workflow as well, like inserting a lattice. They got APIs for that, cutting the lattice according to a solid. Meshing is also, or mesh offsetting is also useful when you have a solid and you know that the thermal characteristics of that, as you print it, there's going to be a percentage of shrink. Well, how do I build that and offset it so that I can accommodate for that? So another very, very specific workflow and a set of tools within Polygonica to address that. Simplification, we see polygonal data getting heavier and heavier, having hundreds of thousands, millions, tens of millions, hundreds of millions of triangles potentially. How do we simplify that? And so we want to simplify that again. We can have a target set of triangles. We also could have a percentage that we want to remove. So simplification is one of their tools. They have a number of analysis tools. Wall thickness is a good example of a new tool they've added. Is this wall too thin to manufacture using an additive process? And then feature detection. It's given a mesh. Where are my planes? Where are my cylinders? What type of information can we get out of my mesh? Now, let's see if we have any questions. Looks like we have one chat before I move on. And the question is, can Polygonica create a quadrilateral mesh? The answer is yes. So I like talking about triangles because my background is visualization, and in graphics we use a lot of triangles. Yeah, but you can certainly create complicated meshes. All right, so where are some places that we're seeing Polygonica being used? Well, additive manufacturing, one of the major markets, and kind of in that space, we also see dental and medical. And so there's a lot of dental implants being printed. That's quite a large market. Renishaw here is doing that, being able to take models and print them for the dental market. There is printing going on in kind of the medical market at large. There's also a lot of mesh data that needs processing in the medical market. So it might not be specific to 3D printing, but the type of data that's coming out of those file formats, needing to visualize it in the medical market is also, we're seeing more uses for polygonal and mesh modeling there. Outside of manufacturing, let's say additive, dental, medical, we also have a number of different partners using Polygonica to simplify meshes for visualization. And so when you think about driving an application for desktop, for mobile, for web, for AR and VR, many times you're needing to see the data. We're visual, we interpret things in a visual way. And since the data, the meshes are getting larger and larger, and the models in general in CAD and building and construction are getting larger and larger, being able to simplify those models is important, because we still can't visualize the largest of these models on desktop, on mobile, in the web browser, or there's a lot of restraints in terms of what you can visualize in AR and VR. The models need to be simplified. They need to be, internal objects need to be removed, and there's a process called shrink wrapping that gives you just an exterior shell for a much larger, more complicated model. So again, Polygonica is able to offer that type of feature functionality for simplifying models, and it works very well into that tool chain and that workflow, being able to prepare models for visualization. In robotics, so one of the powers of this API is if you have numerous solids, it very quickly is able to determine if they're interfering with one another. And that's important for robotics, because you wouldn't want to drive a robot arm into, in this case, in our image here, into the car body. And so can I simulate how this robotic arm is operating and do a lot of clash detection, which Polygonica does very quickly in our simulation step, such that when I upload the program and actually execute it in the real world, we are confident that that doesn't happen. And then lastly, building and construction. Again, these models are becoming heavier and heavier in terms of the sheer volume, so simplification is important there. But also when you're building a building, you have a number of different building domains. You might have structural data, you might have HVAC, heating and ventilation data, you might have piping, electrical. All of these are coming from different systems and are being combined into one single model. And sometimes they don't always mesh. They don't always fit over each other in as well designed as it might be. You may have a structural pillar that is being intersected with some HVAC ducts, and that can't be built. So you have to create an engineering change order, tell engineering, hey, you got to reroute this something. Those intersections can be very easily calculated using Polygonica, again, given the data that exists in the model. So being able to figure out those clashes and provide a list to the users in their software very quickly, another use for the markets. So I'm going to mention this quickly. We're going to go look at some code and look at the package in a minute here. But if you do want to take a deeper dive, we're not going to be follow along coding with me today, but if you want to do a deeper dive of the technology, we do encourage you to sign up for an evaluation, a 60-day evaluation of Polygonica or our other toolkits, and that allows you to look at the toolkit, be able to drive it for 60 days, have access to the API, use your own data, and then build a proof of concept with one of our consulting engineers that steps you through applying those workflows and using the API to see if that's something that you can use within your software that you're developing. So that's pretty much it for the high-level presentation. Before I continue, are there any questions? We're going to look at the install, we're going to look at some of the sample projects, and then we're going to write some code. But I'm going to just let people kind of mull on that. Feel free to ask them in the chat. All right, let's see, and we have a nice crowd here today. About 33. That's a good crowd. Let's see. So let's first take a look at the SDK. So we're gonna go to install. So you'll get an executable. If you sign up for that evaluation, you'll get an executable as well as a serial number that allows you to install the package. It's available for Unix, for Mac OS as well as Windows. We'll be looking at our Windows install today, but it's going to be very similar throughout the different packages. In addition to that, you're going to get a license key that's going to enable you to run the product for a select period of time. And so after you do the install, it is important to put that license key here in our include directory. So I have one that I've placed here that allows me to initialize the SDK and run the sample project. It allows me to create my own sample project and link to it and use the SDK. So let's take a look at what comes in the install. So as part of the installer, you can choose a number of different Visual Studio versions to install if you want. Right now, I'm going to be running Visual Studio 2019. The way in which the DLLs are distributed right now, the DLLs link against Visual Studio version, it's VC 140, which is Visual Studio 2015. We can target that with Visual Studio 2017, Visual Studio 2019. So it's easy to just build a project, but that is one constraint that we have to make sure we hit. But here's the DLLs that I'll be linking against. Here, MS14. So that's my build. We have the DLLs here. We also have documentation, and this is a big one that it all kind of sits within this PDF in the programmer's guide, and we'll take a look at that in just a second as well. The documentation there. We have our include. In addition to the license key, we have a major include file here, the Polygonica API, as well as Polygonica render if you want to be using some of their rendering functionality. You don't have to. So they do have a set of routines that allow you to visualize using OpenGL the results of their output or different steps along the way of processing the data. You're more than welcome to use that. We also at TechSoft, since we are a graphics company, we use our kind of internal graphics library, Hoops Visualize, which sits on top of OpenGL, but also sits on top of DirectX and other kind of lower level technology. We use that for visualization. You can use your own, maybe you have your own OpenGL implemented visualization engine. So it's kind of agnostic. You don't need to use these tools, but they're there and they're useful. We have our libraries that we can link against here. I'm using Windows. So this would allow me different versions, either to statically or dynamically link, debug, or release versions. I think I'm using right now these debug DLLs, either one that is just Polygonica API or one that has Polygonica's OpenGL implementation in there as well. Which programming languages works well? So I have a question. Thanks. Which programming language works well or recommended with Hoops and Polygonica? Good question. C#, C++. My recommendation would be C++. If you want to use Hoops with it, you depending on what of Hoops, right? Hoops is a brand name, so we have Hoops Exchange, we have Hoops Visualize. Hoops Exchange allows you to read data. Hoops Visualize allows you to visualize the data. We have C and C++ and even some C# wrappers for those. But if I was to develop all right, thanks, Hoops Visualize. My recommendation is to use the modern Hoops Visualize interface, which is C++. Polygonica is C++, C, C++. I'd recommend using C++. We have people using C#, and you'd have to wrap things. And with Hoops Visualize, we have full wrappers, but I'm not aware of one for Polygonica, so that would be up to you. Richard, please correct me if you have a C# wrapper. I know we have Richard Baxter online today.
Hi, Jonathan. Yeah, no, there's no C# wrapper as such, but there's lots of companies using Polygonica with C#, and generally what I tend to recommend is you write your own kind of interface layer, sort of application-focused DLL based on top of it in C++, and then wrap that with C#, which there's lots of automatic tools that can help with that. And that, you know, that helps you work around some of the potential performance issues you might get with that, and it gives you a little bit more control rather than us providing a C# wrapper out of the box. But I think it's something that we might look at in the future. But so far, we don't know of any companies where it's really held them back that we don't have a C# wrapper. The API is pretty straightforward to use.
Great. Thanks for that, Richard. Thanks for your question. Another question. You can also, thanks, no, statement. You can also use C++ CLI to talk to C++ code from C#. Thanks, Dave, for that. And then one of the things too we've noticed is many times this is all these APIs. So Polygonica, the Hoops APIs, they're extensive, and many times you end up using just a subset, and just to wrap the functions that you want, if you were to use it in C#, is not you don't have to wrap the whole API. You're wrapping just very specific areas which you're leveraging. All right, and then the last bit that we're going to look at is this source directory, which includes a number of samples, and we'll be looking at some of these, but the majority of these of your different workflows, like remeshing or shrink wrapping or simplifying or doing Booleans, like that's all here. So the code exists, and we're gonna look at that in a minute after we look at our documentation. So all sample code here that allows you to kind of use with sample data, use the API and see how the API works. So let's take a look at some of our documentation here. So we have our programmer's guide, and I wanted to share a couple different areas of interest. So it's quite extensive. We start with programming overview. These are the important ones. So basically getting started with Polygonica, the program structure, the error handling, and journaling. So let's take a look at some of these. So these are important if you're going to be starting up the program. So you need to initialize Polygonica using this API. You give it a license. You give it some options. And most of our function calls are like that, where you have the function call, you pass in or take out data, and you also have some options. Please be careful when you're using this and looking at the documentation. Many times these option structures need to be initialized, and that'll be called out in the documentation. Other times the options don't need to be passed in, and the default options are just fine in the documentation. They'll tell you what the default options are, and you can pass in just a null pointer if that's the case. Many times, and the documentation will tell you that. Additionally, and here's a case. So we don't pass in any options. We just pass in a license key that we get from our license key file. So that's been defined in our license key file. You also need to create an environment. And at the end of your program, you need to destroy that environment and terminate. Part of all of this, in addition, many times you want some feedback, and that's done through our error handling function. So when you set up, after you set up your environments, you create a callback function called whatever you want to call it. You pass in a pointer to that function that handles all of your error handling and output, however you want to handle errors within your application. And there's kind of a long list of different errors that can occur and give you feedback there. Here's an example of that error function, just parsing that out and printing it to the console. And then kind of like a last part of setup, which is quite useful, is journaling. And so when you do run into a problem and it can't be diagnosed using the error function, and you want to be able to replicate that and provide that to support either TechSoft, kind of your first line of support if you do license through us, or through MachineWorks and Polygonica, a journal file is extremely useful because it takes you through step by step as you're journaling. It kind of creates a flat file with all of the API calls, and it allows us to play through exactly what's happened to kind of get you to an error state, figure out why it's there, and very, very quickly diagnose the problem and potentially fix a bug in the SDK. We're not claiming to be perfect, but we do have a high level of success. But we found that extremely useful, so you should be aware of that. It does come at a performance hit, so many times this is something you just enable for debugging, or just enable in let's say a debug mode within your application, or in a debug build. So there's more there about multi-threading and registering threads before and after you make calls. But let's look at one of our applications. So we'll look at, there's kind of two different flavors here. We have some plain ones, and we're going to be looking at simple and adding code to that. And then we have some rendered ones that uses the Polygonica OpenGL display mechanism. And so let's just show an example of that. So I'm gonna build fill holes, which I built recently, and then let's go and let's run this. And so the two things will come up: a console window, and then a display window that includes some graphical output, just to show you the results. So the first thing that we're going to do is load kind of our quintessential bunny. It's flat shaded, so we can get more fancy when it comes to graphics, but it resembles a bunny, kind of classic in computer graphics. Unfortunately, the scan that was made from this, let's say it came from a point scan, has some missing data. So we have holes within that, and we're gonna call a set of APIs from Polygonica to fix that. And so most of these applications here in the rendering kind of step you through, kind of do this, then do this, and then do this, and accuse you in one way or another. In this case, it says press any key to fill the holes using the default option. So we're just calling fill holes, and we're able to do that. So we've now added to this mesh these holes are now filled. We can kind of go back and forth between the before and the after. And it steps you through simplification in numerous different ways, kind of shows you different flavors of calling those functions in these different ones. But what we want to look at, let's roll it back. All right, so that's just graphics. Let's roll it back and look at one of these applications. We're going to change it a little bit. So the first thing is we're looking at simple, and let's run it and run this one, and then we'll walk through the code and we'll talk about it and try to change it up a little bit. All right, so it says in Polygonica initialize. That's great. First step, it's always good. License key works. We're able to create the environment, and we're going to load two solids. So these are two STL files, And let's take a look at these. There's solid 1 and solid 2. And I have another, thanks to Polygonica, I have another little application here called PG Fixer, which is based on their technology. And it just allows me to look at them, look at these STL files using their technology. So let's take a quick look at this. So we have solid 1. Let's pull this over. And it's just kind of like this set of triangles, but it's got some gaping holes there. The same thing with solid 2. And it's a different model. With, you know, at one point it might have been solid, but it's not, right? So we got some holes. We gotta move those edges next to each other. So what we want to do, the goal of this, well, let's step through. First thing we do is before we can do any operations, we gotta fix those solids. Number one, we gotta fill the holes. So that's the first thing it does. Second thing it does is take those two solids and creates a Boolean union of the two of them. And it creates this file called solid.off. And that should be, let's see here, come back to Polygonica, go to bin. So where this actual application is running, we should, oh, where did that go? Maybe in my samples. All right, so here's my file called solid.off. We just wrote it. And we can pull that in. And it shows a watertight mesh of those two different objects that has been Booleaned together. So that kind of gets me, that's where we're going. But let's look at the code. Let's see how we got there. So I'm going to come back. And let's walk through our code here. All right, so the first thing we need to do is here in our main function, we have an environment variable that we're going to create. We have some options. We're not creating our journal. I declared this preprocessor constant, then we would be creating a journal. We initialize our options, and then we call PF initialize with our application, passing in the license key and the options. The next thing we do is create an environment from which we can work in, and also do an error check. So all of these functions do return a value, and we have a macro here called check for error. Basically, we look at this, pretty common one that we use. We just check it for status, and if it's not okay, we terminate. We call destroy my environment, terminate, and then just cancel out of my main function. So that takes care of initialization for us. Same thing happens if we actually get through the application, which we did. We destroy the environment and we terminate the instance of Polygonica as well, do any cleanup and memory deallocation that's necessary. All right, the next thing though is the real meat of the program. And here we're calling load solid 1, load solid 2. And we have a number of two functions here called load and close. So let's go look at that function. So we do a little bit of file name parsing that kind of takes where Polygonica is installed and applies that to the path that we passed in, just gives it a fully qualified path. But the next thing we do is we open up a stream for reading. So that's our STL file. And then we create a couple different options. quiet. And then we read. So we call pf read in the STL data from the stream, given those options, into a solid. And so there's a number in Polygonica, there's a number of different types you can operate on. We're going to be working primarily with the solid type today. There's meshes, and there's faces, and there's vertices. Within the context of today, we're not going to do a deep dive into all of those. But a solid is essentially a collection of polygons. They can be connected, but they don't have to be. And it's kind of the basis for which we do operations on. So in this case, we load in whatever my file format or file is, that STL file, I load it into a solid. And then we ask for some information about that solid. So here we have entity get Boolean property. So we give it the solid, and we say, hey, is this closed? Is this file closed? And we looked at it, we kind of visually inspected it in that TG Fixer application. And between our triangles, there was gaps, there was huge holes. And so the answer is no. If I kind of come through here, both of those needed some work. So I'm gonna debug a little bit. Why did my breakpoint not get hit? All right, so here we are. TF entity get Boolean property. We can ask it for other data. For instance, the next line 108, we ask it, all right, now that we determined, well, let's just try this. So we call that, it returns that it's not closed. So not this. So we need to do some work. We need to close it. We've closed it. So now that solid in memory has been applied to that solid. It now is closed. And we ask it for another property. We ask, hey, is this mesh, does it have self-intersections? So it might be closed, but the result of that, or even the data itself, there may be triangles or polygons that are intersecting with one another, and that could be an error. That's one of the things in which we try to heal using Polygonica. And so that's the next question is does this model have self-intersections? Take a look at that. It does not have self-intersections, so we don't have to heal that. If we needed to, we would call another function fixing those self-intersections. There's other ways in which you can heal your data. The triangles or polygons might, the orientation of the edges in which they're declared may be in opposition to one another. So normally you declare a triangle like vertex 1, vertex 2, vertex 3, and they kind of go in a circle in the same direction throughout your mesh. And you can say it's either left-handed or right-handed oriented, but sometimes they go in reversed ways. So you might have a right-handed triangle next to a left-handed triangle in which the vertices are indexed differently. And so again, another one of these fix functions allows you to fix the orientation of your vertices. You can fix non-manifold edges. You can remove noise shells. So it's a lot of different functionality to prepare your data for downstream workflows. All right, so We closed it. We made sure we didn't have any self-intersections. We're good. We call pf stream close. That closes the file, cleans that up, returns the solid. And then we step through again. We do the same thing for solid 2. It also has open edges, has holes, so we close it. The result of that was some self-intersecting triangles were created. So let's also fix the self-intersections. Close the stream, return the solid. And the result of that worked. We're given a prompt to the user. And then the next thing we do is call pf solid union, taking both of those arguments, solid 1 and solid 2. We union them together using that Boolean operation. Complete it, call it good. And in this case, we write it out as an OFF file, which is a Polygonica file format. There's different ways that we can write out files. I'm going to show you how to write out an STL file now. What this takes is actually a callback function that says walk all of the triangles in that solid, and every time you get some data, launch this callback function. That callback function then writes the data that it receives from Polygonica to a file, and then close that output. We're gonna close this up and again, let's take a look at the results of that simple mesh operation. So I'm going to come GG Fixer, open this up. Just the results. We healed the 2 files, Boolean them together. Well, what if I wanted to write this out to an STL file to use for my 3D printer? Well, let's take a look at that, and that's going to require some documentation. So I'm going to come back up here, go to my contents, and I'm going to look at the geometry export, and we're going to look at exporting solids to STL. So looks like we're going to use this function called tf solid write. It takes a solid, takes a format that we want to write to. So let's use that. So let's start here. I'm going to copy this. I'm going to go back to my application examples. We're not going to use this write code, but instead we're going to pf solid write. And we know it returns a status. So let's set status there. We were writing the result of solid 1. So when we Boolean them together, they stuck the results into solid 1. We need a format. All right, let's take a look at what our format options are. Looks like I can write ASCII STL or binary STL. Let's write it in binary form. So we'll just pass in this constant. We need a stream, so we have to figure out how to create that stream, and we need some options. So before I look at the stream, let's look at what my options are. So options says a null pointer can be passed in. I could have progress. I could include some app data. I could include a header. I'm just going to pass in null for right now. So we're going to pass in null. Make sure we have a semicolon. We still need this stream object. So let's figure out how to create that. So let's see what it has to say. So under PT stream, it should have been opened using this PF stream open. All right, well, let's add that and figure out what PF stream open does. So I'm just going to copy that, and I'm just going to do a quick search. I could go to the index if I wanted to. I want to do PF stream open, and that's part of the journal. But here's section 310 streams. So we have this PF stream open. So let's copy that, and yeah, we'll just do that. We'll give it a status. Status equals PF stream open. We're going to give it a file name. Let's just call this solid.stl. And then the operation type looks like we want PV file write because we're writing a file. So let's put that in. Some options. Let's see what we got for options here. Contains a single field, file name. All right, so it does look like we need to create some options. Let's do that for safety, but it also defaults, it just is telling me to use wide character. I haven't tried it with a null. Guess we could. Let's just do that. We're going to give it options and call this stream options. And it needs to be passed in by reference. Whew. And then the last thing here is stream. Again, that needs to be passed in by reference as well. And a semicolon. And we can do some error checking here. So we can check for an error. We can say failed to open file for output. And then we can do the same here. We could say failed to write file. And let's see what else we got. Probably should close the stream. So let's look back here. We also want to close the stream. So let's do that. Close stream. Close stream. All right. And done. So I'm going to build that. And let's run it. So we can kind of step through. So I have a breakpoint there. I do. Let's just walk through that. And let's look at our output. So 1055, we have solid.stl. And I can open up PG Fixer again. We can take a look at that. Bring in STL. Same file, now it's an STL file, and I can bring that to other applications. For instance, we have couple here that I wanted to show you. We have something that is based on Hoops Exchange for reading data and Hoops Visualize for visualizing data. So we can do the same thing, and then of course Polygonica to be operating on that data. So I could take that STL file and I could bring it in to this application or any other application. And so that was at let's see, we were in third party, Polygonica 2.3, source, samples, simple, objects, visualize with this visualize. We can do some other things, some other interesting things here. Let's load in a different file using Hoops Exchange, another STL. So I have some data here. I just want to show you, I want to show you how easy it is to code Polygonica. We showed you how to save a file. Showed you how the API to heal it. I said I was going to simplify it. We'll kind of look at that here. Actually, we'll get there. So let's look at some data. I got a bunch of data here, 3D printing. A more complicated file, like 50,000 triangles. Still, it has a hole, right? So green edge is a hole. Red triangles are intersecting triangles. But we can kind of run the same functionality that's integrated with this application. We could run it using some Polygonica calls. We can just auto heal it. So that filled in those holes, it removed those intersecting triangles. If there were non-manifold triangles, it would do the same. And let's say we want to simplify. So simplify by 50%. Right now, you'll notice there's 50,000 faces. We'll run this on it. Simplifies it to 25,000 faces. Or I can do some other things with Polygonica, like slicing it. So slice it along the y-axis. Let's do it every 5, whatever units this is declared in. We slice it in those units you define in your own application. Using Hoops Exchange, if there's units in the CAD file, because we can read over 30 different file formats from CAD vendors, we kind of provide you that information. All right, so we talked about Polygonica, what it is, how to use it, looked at the API, looked at the install, wrote a little bit of code. The last thing I wanted to do is to show a couple different applications and different things you can do with Polygonica. So we showed that desktop application. We also have one using Hoops Communicator, kind of running in the cloud. So we can do stuff like, let me bring in some CAD data in this case. So we look at some of our Hoops Exchange sample data. I'm going to bring in samples, look at Exchange, I want data. Here we are. Data, how about some CATIA data? And let's see if we can load in something. So using Hoops Exchange, we upload that file to a server. Does it have any errors? Because we do a pretty good job reading data. Yeah, so it doesn't have any errors, unfortunately. We'll have to bring in some dirtier data, but we were able to load it using Hoops Exchange on a server, map it to Polygonica, bring down all the triangles, visualize it with Hoops Communicator, and present it here within this web viewer, and also analyze it with Polygonica. It says, yeah, we're closed, we're manifold, we don't have intersections, we have the correct orientation of our triangles. Let's bring in that Lorana data set, that STL file, and try to heal it using the same set of tools. So I'm going to upload that. And in this case, we have a hole, we have the same intersecting triangles. We can call the same heal function from Polygonica and fix all of those errors and prepare it for 3D printing. The last thing I wanted to show you, if you want to get going with, sorry, that's the wrong website. If you want to get going with Hoops Exchange to read data, and then Polygonica to heal it, we do have some sample code to kind of get you started using our toolkits here on the Innovation Lab. So we go back to that. So Innovation Lab, this is code and projects that aren't specifically supported by engineering and fully tested, so they're experimental, but we found it useful. So there is some code here that loads data using Hoops Exchange. It has a set of classes there that kind of walk through all of your mesh data. You can bring that data in from over 30 different file formats, CAD file formats. You'll get all the mesh data, bring it into Polygonica, operate it on it using Polygonica, and then use it within your application. So it's just kind of like a getting started with rich CAD data, not just STL or your own mesh data. So that's kind of a quick overview of the Polygonica toolkit, looking at some of the code, stepping you through. We're really happy to have you guys here today as part of our community. Thanks for sticking with us. If you want to kind of go to the next step, we really encourage you to do that, to look at the SDKs. Please sign up for an evaluation at techsoft3d.com, and that gives you access to the toolkits for 60 days. You're able to work with one of our consulting engineers, so that's a software engineer that steps you through how to navigate the advanced functionality of Polygonica. We also can couple that with other complementary toolkits like Hoops Exchange to read CAD data, Hoops Visualize, or Hoops Communicator to visualize that, or even Hoops Publish to publish it to 3D PDF or 3MF or STEP or STL or whatever you want, wherever you want to go with that. So that's all I have for you today. Thank you so much for your time. I'd be happy to stick around if you have questions about particular workflows. I know we just went a few minutes over. That seems to be the theme for these technical training seminars. The other content is up there on our website, or excuse me, on our YouTube channel. The different training seminars that we've had over the last few weeks, as well as our Hoop Summits. They talk about our different products and manufacturing in the digital factory. But I'll leave it open if you have any other questions. I hope, I think I was talking to Tim, who is calling in from his garden in the UK. I hope you have an enjoyable evening and the weather improves for you there in the UK and in Europe in general. Thanks for staying up a little late with us. I hope it was informative. There will be a survey that kind of goes out in a few days, as well as a link to this video. If you could just take a minute to fill out that survey to let me know if you found this useful or not, I would appreciate that, or any additional feedback. We want to make these valuable to you. So if that's, I don't see any other questions here in the chat. All right, thanks Tim, thanks Dave, thanks Li Ming. It's good to see you guys. Well, if that's it, I wish everyone, wherever you are calling in from today, a good afternoon, a good morning here on the West Coast US. It's still morning, but again, thank you so much. Stay well, stay safe, everyone out there, and we look forward to seeing you either here in the virtual world or hopefully sometime soon in person. All right, take care, everyone.